Okay, so to understand the square root function, we're going to start with the parent function, which is just the square root of x. And to start off, you're going to create a table of values for this interval from -1 to 9. So I've drawn what this will look like here. You'll obviously want to have 5, 6, 7, 8 in between 4 and 9 here, and the corresponding y values. Then go ahead and work through b, c, and d as well, and then we'll take a look at it briefly together. Okay, so let's start off with just the table and noting some of the things that we get from the table. The first is, of course, you can't take the square root of a negative number. That's going to be the imaginary number I, which is not real. So that's not going to show up on our graph here. And the points that we're going to be able to use that make the most sense to use are the ones where we actually have a square root that is a whole number, a perfect square. So 0, square root of 0 is 0. 4, square root of 4 is 2. 9, square root of 9 is 3. And if we use those points, it's going to be a lot easier for us to plot those points, obviously. Alright, so at this point, let's consider what the domain of the function is so that we know all the x values where we can graph the function and also the ones where we can't. As we saw here, when x is a negative value, we get a non-real answer. So anytime the radicand is negative, we won't have a defined real value. And this means that our domain are going to be all x values greater than or equal to 0, right? That excludes all of the negative x values. All right, at this point, we now know where we can graph our function, and we get a basic shape by looking at the points that we have plotted. So I can simply draw a nice smooth curve through those points there, and I can imagine, look, it's going to continue going on, right? I know, for example, when x is 16, the y value is going to be 4, and so on and so forth. Now I want to consider the shape of the radical function here, and what you'll notice is this looks very similar to a parabola, except that it's on its side. So it's half of a parabola on its side, and that should make sense based on what we've talked about with radical functions, the square root function being the inverse of squaring. So that's the basic shape, and if you really want to challenge, think about how the rate of change is changing as we move along our function, particularly paying attention to the slope between 2 points. All right, let's go ahead and get down some of these key points, and then we'll continue graphing. All right, so when dealing with a square root function, there's a couple things we want to keep in mind. First and foremost, when you hear the term radical function, that's just a function that has a variable in its radicand, as the square root function does. The domain for our square root function will not include any values that result in a negative radicand. So when we looked at our domain, it was x greater than or equal to 0, because any x value less than 0 would make our radicand negative, and therefore we'd have an imaginary output. Also, the basic shape of a square root function is half a parabola on its side, and this is of course because the square root function is the inverse of the square function, or the quadratic. Alright, so our goal is going to be to pinpoint a way for us to actually graph these without making a table. So we're going to try and look at just the domain and think about the x-intercepts and the y-intercepts, and hopefully with that in mind be able to just graph our radical functions. So let's take a look. Okay, so let's start here. We're going to, for each function, identify the domain, find the x and y-intercepts, and then sketch the graph of the function. Okay? So we'll do this one together. We've already done this, but I'm going to show us how this process would work here. So the domain, all x values that will make my radicand positive. So that's going to be x greater than or equal to 0. Okay? So I know that my function is going to be defined everywhere to the right of my y-axis. The x and y-intercepts, well, these I can do really in my head here. If I set my y value equal to 0, I set my function equal to 0, the x value that I need to make that happen is x equals 0. I can show that work here. If I set square root of x equal to 0, then I'm going to square both sides, and I'm going to get x equals 0 squared, which is still 0. Similarly, for my y-intercept, if I input a value of 0 for x, I just have the square root of 0, which is again 0. So I can see that my root and my y-intercept are the same. And then I can go ahead and sketch the graph of the function because I know some of the values. I can plug in, for example, something like 9, and I'll get a value of 3. I could plug in a value of like 16, and I'll get a value of 4. Okay? So let's try and do the same thing here. Let's take a look at g of x. I'll use a different color. First off, let's think about the domain. Well, the domain are going to be all the x values that will keep my radicand positive. So what would make this radicand negative? Well, let's think about it. If we had 0, we'd have 0 minus 2. That wouldn't work. If we had 1, we'd still have negative in our radicand because 1 minus 2 is negative. What's the point at which we will finally break out of the negative numbers? That will be when x hits 2. Once x is equal to 2, then we're going to be good to go. Everything past that point will give me a positive radicand. So my domain is going to be all x values greater than or equal to positive 2. So when I look at my graph here, I realize that this function isn't going to be graphed anywhere to the left of 2. In fact, when x is equal to 2, that's going to make my y value 0. So that's where my root is going to occur. And there are no y-intercepts. If I plug in 0 for x here, I'm going to get square root of negative 2, which is an imaginary number. And of course, we know the basic shape of our square root function. So we can actually go ahead and sketch a nice little graph of g of x. All right, your goal is to go ahead and do the same thing for these next two functions, h and p. Notice a key difference here. In g of x, we had a radicand of x minus 2. Here, we have a square root of x, and then after taking the square root, we're subtracting 2. So be mindful of those differences. Do your best to sketch both graphs, incorporating the domain, the x and y intercepts, and for these two, explain how those graphs are different from the parent function. So in this example, I might say that this graph is different from the parent function in that it has been translated 2 units to the right. All right, we'll take a look at both of those tomorrow.